Hi everyone, my name is Oksana and I'm a postdoctoral researcher at Nordita in Stockholm. And today I'm going to tell you about signatures from axion inflation with non-Abelian gauge fields. So first of all, thank you to the organizers for this opportunity. So my talk is about parity-evaluated dynamics in the early universe, in particular during inflation, and I will tell you how this parity-evaluated dynamics can generate multi-messenger signals in scalar perturbation, gravitational waves, and primordial magnetic fields, though mostly I will focus on the last two. And as a bonus, I will also flash the Schwinger effect during axion inflation. So to start with, axion is the main player of my talk today, and it's coupled to non-Abelian gauge fields. So what is the mechanism that I'm going to talk about? The mechanism is the following. So when axion rolls down its potential during inflation, it gains some velocity. And due to its coupling to gauge fields, it produces tensor perturbation or gauge field tensor modes. When it rolls faster, it produces even more gauge field modes that at some point can backreact onto the background solution of an axion by itself and change its dynamics. So this is called backreaction effect in axion inflation. And I will show you during my talk how this backreaction effects can lead to correlated signal in primordial gravitational waves and primordial magnetic fields. So, of course, one of the main motivations for the presence of the gauge fields is the sourcing of gravitational waves. And here you can see the equation of motion for gravitational waves, where on the right-hand side, there is a source contribution that is also called anisotropic stress tensor, and there are multiple ways to source the anisotropic stress tensor, but I'm going to focus on the gauge fields. And this is an example here how the gravitational wave signal can be enhanced for axion coupling with non-Abelian gauge fields in such way that it can be observed in future observations. But not only gravitational waves, such parity-evaluated dynamics involving axions in the gauge field, it can also lead to specific B-mode polarization in the CMB and produce parity-odd CMB correlations, such as TB and EB correlator that is usually zero in the parity even case. Additionally to that, it can produce chiral gravitational waves when one polarization is different from another. In addition to that, it also can produce tensor non-Gaussianity, and you can see an example of the sensitivity for future LiteBIRD mission to probe this tensor non-Gaussianity. But there are also some problems with the presence of the gauge fields in the very early universe. And the main problem is that the gauge field would dilute because during the exponential expansion of the universe, during inflation, the vector potential dilutes like 1/a, where a is a scale factor. So in order for the gauge field not to dilute, it has to couple to some other field. And such possibility could be coupling to scalar field, to pseudoscalar fields such as an axion, or introduction of more higher order operators that would sustain the gauge fields during exponential expansion. So today I'm going to focus on spectator Hromonetian inflation model that has axion sector, where chi is an axion with a cosine potential, and an axion is coupled to a non-Abelian gauge field. So axion together with a gauge field is a spectator. It means that it has a subdominant energy density with respect to some other inflaton field that is responsible for driving inflation, and in this case, for producing scalar perturbations in the CMB. So again, at menu here is a non-Abelian gauge field. And it has been known since more than 10 years now that such a configuration possesses a homogeneous and isotropic attractor solution for the background. So it's given by this configuration where Q is a function of time. It's a vacuum expectation value of the gauge field. And in this case, we have multiple scalar perturbations. So we have scalar perturbations of inflaton, delta phi, scalar perturbations coming from an axion, from the gauge field, and the metric. And in this case, as I mentioned, the inflaton is mainly responsible for the CMB. But we will see later that the gauge field can also contribute to production of primordial black holes. So in this talk, I will focus mostly on tensor perturbations, and there are two different tensor perturbations in this case. So there are tensor perturbations of the metric. I will call them psi, and they are responsible for gravitational wave production. And also there are tensor perturbations of the gauge field. I will call them capital T, R, and L. R and L stands for right and left polarization. And tensor perturbations are responsible for primordial gravitational waves and primordial magnetic fields. So now let me tell you about the mechanism to produce chiral gravitational waves here. So here you can see an equation of motion for tensor modes of the gauge field for the right and left polarization. And the main point is that the effective frequency in this equation, it depends on polarization. So there are parameters MQ and Xi. These parameters depend on the velocity of an axion and on the wave of the gauge field. But for some combination of these parameters, the effective frequency can become negative. And if it gets negative, then only one of the polarizations of the gauge field gets tachyonically it gets tachyonic instability. And this you can see on this plot. So this is the plot for the gauge field perturbations, right and left polarization. And you can see that only right polarization is getting exponentially enhanced, and the left polarization remains in its vacuum. So it means that at every time step, only one polarization getting excited, and it leads to the presence of chirality in the system. So because of the presence of this chirality, on the right-hand side, we would have a chiral source that would produce chiral gravitational waves, meaning that only one polarization of the gravitational waves would be enhanced with respect to another polarization. So this is the main point. But the problem is the viability of the parameter space in this particular axion-SU2 coupling. So here you can see the parameter space spanned by G, which is the gauge field coupling of a non-Abelian gauge field, versus parameter MQ that controls the amplification of the gauge field modes. And this shaded orange area shows that there is no amplification of gravitational waves. It means that it's not very much observationally interesting to look in that area. The blue shaded area corresponds to overproduction of scalar perturbations in the CMB, so it's also excluded. And the green shaded area corresponds to the strong backreaction regime, where we cannot neglect the backreaction from the produced tensor perturbations. So the only viable area remains this small pink triangle. But the problem is that if we'd like to compute the magnetogenesis from this model, we have to associate our SU2 field with Z and W boson of the standard model that have gauge field couplings of order 0.65. So this corresponds to the star in the diagram. So we are getting inevitably to a strong backreaction regime. And this was actually the main motivation for us to study the backreaction regime in axion-SU2 inflation. So in order to study it, we use this fiducial parameter that come step by step to a strong backreaction regime. And we use the pencil code to implement this dynamics. So this is what we have found. So here you can see the evolution of the Q. This is wave of the gauge field with respect to the number of e-folds for different values of the parameter MQ that controls the amplification of the gauge field. For a very small value of MQ, we see that wave stays constant. This is because of assumption of a constant Hubble parameter, but nevertheless, we don't see any back reaction onto the background solution of the gauge field. But if we start to increase MQ, we see that there is some bump that appears, and then the solution converges to the negative values of the wave of the gauge field. So if we increase MQ further, the bump happens earlier, and we converge even to more negative values of the gauge field. And we also see changes in the dynamics of an axion field. So we can see that the slope changes for an axion. So we found that in the strong backreaction regime, system enters into a new attractor solution with negative values of the vacuum expectation values of the gauge fields. And the transition to the backreaction regime, it can generate the special oscillatory features in gravitational waves. So here you can see an example of 3 different curves for the gravitational waves that we have found. So the peculiarity in these oscillations that descend from the peculiar oscillatory features in the oscillations of the tensor modes. An important point that the peak in the gravitational wave power spectra depends on the moment to the transition to the backreaction regime. So depending on the moment when this transition happens during inflation, this peak can be moved to the left or to the right. So if it happens earlier, this peak of the green curve could move into the sensitivity curve of the future interferometer LISA. And interestingly, that such a transition to negative attractor solution can also contribute to generation of primordial black holes. So it has been found by the group of Emma and Dimitri Giovanni that when the solution crosses the negative values of MQ, in particular when MQ is smaller than the square root of 2, then there is an instability in the scalar sector that produces a peak in the power spectrum and can produce primordial black holes as well as produce additional signal in gravitational waves. Now, let me talk about consequences from primordial magnetogenesis. But first of all, why should we care at all about primordial magnetic fields? So blazars are active galactic nuclei in our universe that emit TeV photons. When these TeV photons travel through our universe, they interact with extragalactic background light, think of as starlight. And with this interaction, then they produce electron-positron pairs. Then electron-positron pairs rescatter with CMB background, and in the end, we measure GeV. We should measure GeV photons. So the point is that every TeV blazar should be observed to have GeV halo. But we do not see this secondary GeV halos. And one of the explanations for this non-observation of secondary GeV halos is the presence of primordial magnetic fields in intergalactic voids. So if there is a primordial magnetic field, then the produced electron-positron pairs would be deflected in such a way that they're deflected from our side of view and we do not see them. And there are some lower bounds on primordial magnetic field coming from such a non-observation, and such bounds are currently about 10 to minus 15 Gauss for the correlation lengths of the magnetic field of order megaparsec. So in this plot, there are lower bounds from blazar observation and upper bounds coming from CMB and other measurements. So the allowed area for primordial magnetic field is this white area. So now we can use our results from studies of the strong backreaction regime to understand if it's possible to produce primordial magnetic field from axion-SU2 scenario. So now, finally, we can identify our SU2 gauge field with Z and W bosons of the standard model. And we found that the presence of the backreaction regime is crucial for primordial magnetogenesis because it sustains the tensor perturbations on superhorizon scales. So you can see here the blue curve corresponds to the backreaction regime, and the green curve corresponds to tensor perturbation evolution in the no backreaction regime. And it's clear how much the green curve is suppressed with respect to the blue one. So thanks to the presence of the backreaction, we can sustain our perturbations until the end of inflation, and then we can associate them with perturbations of, let's say, W boson. And we assume that during the electroweak phase transition, there is a standard transformation to a photon through the Weinberg angle. So finally, we can compute the power spectrum of obtained primordial magnetic fields. And here you can see the power spectrum of the magnetic field and the power spectra of gravitational waves for different parameters. So first of all, the magnetic field, again, has the specific oscillatory features. And secondary is that we are necessarily getting correlated signal with primordial magnetic fields and gravitational waves. So if we are getting strong enough signal in magnetic fields, we should expect in observations to get an accompanying system in primordial gravitational waves that makes the possibility of such a detection much higher, which is very exciting. So now we can place our stars in the diagram from blazar observation constraints, and we found that such a primordial magnetogenesis scenarios scenario agrees very well with current bounds. So you can see the stars that corresponds to our fiducial parameters that we studied, and we understand how to move stars in this diagram. So in order to get larger amplitude of primordial magnetic fields, we need to have the gauge field wave reach zero close to the end of inflation. And in order to get a larger coherence length of the magnetic fields, there should be larger instability in tensor perturbations. So the message is that such scenario agrees very well with current bounds coming from Blaser observations. So now what about the back reaction from electric currents? So finally, I would like to tell you about the Schwinger effect. So Schwinger effect is spontaneous creation of electron-positron pairs in the presence of strong electric fields. So this is the estimated critical value for the electric field that has to be reached for this effect to happen. And since during early universe the energies are very high, we expect that we are reaching this critical value, and the Schwinger effect can actually be crucial, especially for primordial magnetogenesis. And in the end, the presence of the electron-positron pairs is expected to screen the produced fields during early universe. So of course, like it's very complicated and non-perturbative effect, and it's very hard to study fermions on Elaris. So we started with the simplest case of axion-U inflation that has been already studied by many groups. I'll just show you the equations of motion here, where we have the back reaction contribution, this E dot B contribution in the equation of motion for an axion. Here, phi is an axion, and also in homogeneous contributions coming from an axion. So now the system is already complicated enough, but in order to study Schwinger effect, we have to complicate it even more. We have to include the charge contribution, charge Lagrangian, that would generate additional current in the system. And there is also the additional contribution coming from the energy density of the produced particles. So in order to take into account the effect from Schwinger pair production, we used an effective current approach that has been developed some years ago already by other groups. So the main complication is that this current has been derived in the scalar form. So in order to use it in the equations of motion, we have to promote it to a vector. And there are some ambiguity in the vector decomposition for the Schwinger currents, but so I don't have time to talk about this now, but please ask me during the question session. So the main point is that the presence of such a Schwinger current leads to significant suppression in the magnetic fields. So here you can see the black curve is the energy density in the electric magnetic field versus the total energy density without Schwinger effect. And the dashed black curve is the same energy density with the Schwinger effect. So we are getting more than 6 order of magnitude suppression that significantly challenges gauge preheating in axion-U model. So additionally, we found that such suppression, it doesn't really depend on the description in the equations of motion, in the sense that it doesn't really matter if it's a linear back reaction or non-linear back reaction. If we're taking into account homogeneous or inhomogeneous contribution coming from the axion, we are getting very similar suppression. So you can see here this red curve corresponds to the linear back reaction case without Schwinger. Black curve corresponds to the fully non-linear back reaction computation without Schwinger. And these 3 curves corresponds to the non-linear linear computations with the Schwinger currents. So we're getting very similar suppression to all cases that allows us to use semi-analytical techniques potentially to estimate the effect of the Schwinger effect. And another point is that Schwinger effect seems to become dominant even before we are reaching to a strong back reaction regime in the system. So in the end, it completely endangers the primordial magnetogenesis from axion inflation, because we are getting more than 2 orders of magnitude of suppression in primordial magnetic field that makes magnetogenesis from axion-U inflation really challenging. So due to the lack of time, I think I stop here, but I'm really looking forward to the question session. Thank you so much for your attention. Bye-bye.